We continue our study on acid-base equilibria, looking at weak acids and weak bases and their properties, and then finishing up with a discussion of Lewis classification of acids and bases. Here's a general approach to handling weak acid-base equilibria. And we'll find out that this approach is actually generalizable to all more complex equilibria. We start off by writing the balanced equation for the reaction involved. We write an expression for the acid dissociation constant. Then we define X as the change in concentration that occurs during the reaction for one of the components. From this, then, we can construct a reaction table in terms of the initial concentrations of our reactants and the change X, and then the final concentrations of all species present. We may want to make assumptions to simplify the calculation in some cases. Then we substitute our values for our concentrations into the acid dissociation constant expression and solve for X. In the end, we look at our value for X and make sure that our assumptions are justified. In general, molar concentrations are indicated by a pair of brackets, and a bracketed formula with no subscript indicates the equilibrium concentration in solution. Our assumptions are that hydronium for autoionization from water is negligible. We can correct this, and there are ways to address it, but we're not going to worry about them right away. And we also assume that the weak acid has a small acid dissociation constant, and its initial concentration, therefore, is approximately equal to the concentration at equilibrium. We can check on this approximation fairly easily using something called the extent of dissociation. When we throw a weak acid in water, a portion of it will dissociate, which we can observe. The percent dissociated is given by the following equation. The dissociated concentration divided by the initial concentration times 100. For a given acid, as the initial acid concentration decreases, the percent dissociation of the acid increases. A decrease in the initial acid concentration does result in a decrease in the dissociated acid concentration, which is equal to the hydronium concentration, which is equal to the conjugate base concentration. So the fraction of the ions present increases, even though the total of our weak acid decreases. For polyprotic systems, which are going to be very important, we see that we have molecules that have more than one ionizable proton. So a polyprotic acid then will have multiple values for the acid dissociation constants, with each step having a unique value decreasing in size monotomically from the most protonated to the fully deprotonated system. Here we have phosphoric acid, an acid that is commonly used to give the slight tart taste to colas. Phosphoric acid is a weak acid, and here we can see the first proton come off with Ka1. Then the dihydrogen phosphate anion produced can lose another proton with Ka2, and then the monohydrogen phosphate dianion can lose the third proton from phosphoric acid with Ka3. We see that, as always, Ka1 is greater than Ka2 is greater than Ka3. When we're calculating concentrations of a hydronium ion produced by various acids, we usually neglect the protons produced after the first dissociation for polyprotic systems, as these are a small correction to the total proton concentration. Here are some Ka values for some common polyprotic acids. Of course, these would be available to you in a table that you would have provided to you. Your textbook has a much more extensive table. You can see the general trends. Now we can take these trends and generalize them. For non-metal hydrides, for example, hydrogen sulfide, H2S, when they dissolve in water, their acid strength depends on the electronegativity of the central nonmetal atom and the strength of the nonmetal hydrogen bond. When we go across a period, the acid strength increases. So if we go across the period, we know that the electronegativity increases so that the acidity of the EH increases. As we go down a group, the acid strength increases because the length of the EH bond increases going down a group, and its bond strength generally tends to decrease. So here are the trends we see for group 16 and group 17 for the second, third, fourth, and fifth rows of the periodic table. We can see that as we go from group 16 to group 17, the acidity increases. And when we go from the second row down to the sixth row, we see that the acidity increases as well. For the oxoacids, all the oxoacids have their acidic hydrogen bonded to an oxygen atom. The acid strength of oxoacids depends on the electronegativity of the central nonmetal atom and the number of oxygen atoms around the central nonmetal atom. For oxoacids that have the same number of oxygen atoms, the acid strength increases as the electronegativity of the central nonmetal atom increases. For oxoacids with different number of oxygen atoms, acid strength increases with the number of oxygen atoms. So, for example, on row A, we have hypoiodous acid, hypobromous acid, and hypochlorous acid. The electronegativity increases from left to right, and so the acidity also increases, with hypochlorous acid being the strongest of those three. On row B, we see hypochlorous acid versus perchloric acid, perchloric acid being a strong acid and hypochlorous acid being a weak acid. More oxygens, higher acidity. We said earlier chloric acid is a strong acid, as is perchloric acid, but perchloric acid is the stronger acid ultimately because it has more oxygens. It turns out that there are some metal ions that are acidic as well. When you put them in water, they can bind to hydroxide to release protons. They go by this reaction. The metal going into water reacts with water, forming the hydrated metal, and then the hydrated metal can release hydronium ion by binding the hydroxide. This is particularly true if Mn plus is small and highly charged, and specifically this is for the trivalent metals, those with a charge of 3. That's usually the highest charge you see in aqueous solution. So aluminum 3, iron 3, chromium 3, these are all small, highly charged ions, and they are all acids in solution. These are important to note because iron, for example, is involved in acid mine drainage when mining for coal mines. When you hit a pyrite deposit to release iron, that iron it has multiple steps, but one of the steps does involve binding to hydroxide and releasing protons. Here we can see the space-filling model for aluminum 3. When it goes into water, it binds 6 water molecules, and it can release a proton to produce the hydroxide form. So aluminum 3 plus is an acid as well. Weak bases are as follows. A Bronsted-Lowry base can accept a proton, as we know. So when we dissolve a weak base at water, we see that it reacts with water to pull in a proton and release hydroxide. We can quantify this using the base dissociation constant, or what's sometimes called the base ionization constant, or the base hydrolysis constant. And so that's written out as following. This is an important equation to remember. Kb, the base dissociation constant, is equal to the conjugate acid concentration times the hydroxide concentration divided by the weak base concentration. We note that no base actually dissociates in solution, but ions are produced when the base reacts with water by hydrolysis. And this important definition, pKb, is equal to minus the log of the base dissociation constant. Kb tells us the strength of the base. Stronger bases produce more hydroxide, which means they have a larger Kb and a smaller pKb. Here are some Kb values for some common amines. Amines are among some of the most common weak bases. Of course, you'd be provided tables for these. Generally, they're part of an acid dissociation constant table, because we'll see that there's a relationship between Kb and Ka. So the anions of weak acids often function as weak bases. So if you have a weak acid that loses a proton, there's an anion left over. But if the anion is somehow introduced into water, it can pull off a proton to release hydroxide. The solution of HA is acidic, while the solution of A- is basic. Hydrogen fluoride, for example, is a weak acid, much weaker than hydronium. So the equilibrium lies to the left here. So we find out that HF goes into water to produce hydronium and fluoride, but the reaction has a small equilibrium constant, so the equilibrium lies to the left. HF is much greater than F-. But H3O plus from hydronium is much greater than hydroxide, so the solution is therefore acid. We can look at it from the perspective of the fluoride. Now, if we take sodium fluoride rather than hydrofluoric acid, we dissolve sodium fluoride in water, it dissolves completely, and then we have fluoride acting as a weak base. Sodium is simply a spectator. So fluoride reacts with water to form HF and OH-. The equilibrium favors the formation of the weaker acid and base, since HF is a stronger acid than H2O is. This equilibrium also lies towards the left. F- is much greater than HF, but OH- from F- is much greater than H3O plus from water. So the solution in this case is basic. We know now, and we'll see, that Ka and Kb for a conjugate acid-base pair have a relationship. And the relationship can be seen as following. If we take the acid dissociation reaction shown in the first row, it'll have an acid dissociation constant. We can take the conjugate base hydrolysis reaction in the second row, which will have an equilibrium constant of Kb. If we add these two reactions together, we end up with the autoionization of water. 2 molecules of H2O goes to H3O plus OH-. And this reaction has an equilibrium constant that we know is Kw. And we learned last chapter that if we add two reactions, then the net reaction is the product of the equilibrium constants. So the overall equation has an equilibrium constant equal to K1 times K2, or Ka times Kb. And we know the result is Kw. Therefore, Ka times Kb equals Kw, or 1 times 10 to the minus 14. That is a very important relationship to remember. So not only does hydrogen ion concentration times hydroxide ion concentration equal to Kw, Ka times Kb also equals Kw. And pKa plus pKb equals 14 if we take log. That's the log on both sides. So this relation is true for any conjugate acid-base pair. So these equations should be recalled, and as far as anyone has been able to measure, these hold correctly. This summarizes the weak acid and weak base equilibria calculations that we do. So first off, we write out the balanced equation and the equilibrium expression. For weak acids, we have an acid dissociation constant. If we dissociate to the extent as x, we can calculate x from this equation here. Solving for x, we can get the hydrogen ion concentration and calculate pH. We can get pOH from that pH by subtracting from 14. On the weak base side, we can do a similar calculation. We can write out a reaction: base plus water gives the conjugate acid plus hydroxide, and Kb is shown. We can solve this for small x, from which we can deduce the hydroxide ion concentration and calculate pOH. And we can use that subtracted from 14 to get the pH. Now let's look at a series of salts that yield neutral solutions. A salt that consists of the cation of a strong base, like sodium hydroxide. So the cation will be sodium. And the anion of a strong acid, like, for example, nitrate for nitric acid. If we take a cation and anion like sodium nitrate, it will give us a neutral solution. So we can take sodium nitrate. Sodium is the cation of sodium hydroxide, which is a strong base. Nitrate is the anion of nitric acid, which is a strong acid. The solution is neutral because neither sodium nor nitrate reacts with water to any significant extent. The ions that do not react with water are the anions of the strong hydrohalic acids, chloride, bromide, and iodide, and the anions of the strong oxoacids, acids such as nitrate and perchlorate. The group 1 cations, sodium, lithium, potassium, rubidium, and cesium. And then the lower group 2, calcium, strontium, and barium. Salts that will yield an acid solution, and we have ammonium chloride as an example. A salt that consists of the cation of a weak base, so ammonium would be the cation of the weak base ammonia, and the anion of a strong acid, so chloride comes from hydrochloric. So ammonium chloride gives us ammonium, which is a weak acid, and chloride, which is not a base. So the solution is slightly acidic because ammonium reacts with water to produce protons. Chloride does not do anything significant. Salts that yield acid solutions, and here we have iron 3 nitrate. If we have a small highly charged metal ion in the cation and an anion of a strong acid, we get an acid solution. So iron 3 nitrate would give us iron 3, which is a small highly charged metal cation, and nitrate, which is the anion of nitric, a strong acid. This solution is acidic because the hydrated iron 3 ion will react with water to produce hydroxide, and nitrate does not. Salts that yield basic solution. These are the anion of a weak acid and the cation of a strong base. So, for example, sodium acetate. Acetate is the anion of acetic acid, which is a weak acid, so acetate is a weak base. Sodium is the cation of sodium hydroxide, and sodium as a cation is sufficiently weak that it is not an acid. This solution, sodium acetate, is basic because the acetate reacts with water to produce hydroxide. Now, what about salts that contain a weakly acid cation and a weakly basic anion? If a salt consists of the cation of weak base and the anion of weak acid, the pH of the solution depends on the relative acid strengths of the base and the acid. We can take, for example, ammonium cyanide. Ammonium is the cation of the weak base ammonia. Cyanide is an anion of the weak acid hydrogen cyanide. So we can see here ammonia giving ammonium, cyanide giving hydrogen cyanide. The reaction proceeds farther to the right, tells us which one will dominate. So if we look at the Ka and the Kb of ammonium and cyanide, we see that the Ka for ammonia is 10 to the minus 10, and the Kb for cyanide is 10 to the minus 5. Since the Kb for cyanide is greater than the Ka for ammonium, cyanide is a stronger base than ammonium is an acid, so the solution is basic. We'll see, you'll see later on, there's actually a simple mathematical trick to calculate fairly closely what the actual pH will be. Now, what about amphiprotic systems? Amphiprotic salts have a cation that comes from a strong base and an anion that comes from a polyprotic acid with one or more ionizable protons still attached. So this can act as an acid and a base. To determine the overall acidity, we have to compare the magnitudes of Ka and Kb for the anion of the salt. And a classic example is sodium monohydrogen phosphate. Sodium is the cation of a strong base, so that doesn't come into play. But monohydrogen phosphate dianion is the second anion of the weak polyprotic acid phosphoric acid. Therefore, it undergoes two reactions. Monohydrogen phosphate can lose one of its protons, and then monohydrogen phosphate can react with water to pick up a proton, acting as a weak base. So, in order to determine what dominates, we look at the Ka and the Kb. The Ka of phosphoric acid is 4.2 times 10 to the minus 13. The Kb of monohydrogen phosphate is 1.6 times 10 to the minus 7. In this case, since Kb is greater than Ka, monohydrogen phosphate dianion is a stronger base than acid. So a sodium monohydrogen phosphate solution is going to be alkaline. The acid-base behavior of salts and water are summarized in this table. And this shows us how to handle cations of a strong base, anions of a strong acid, cation of a weak base, anion of a strong acid, small highly charged metal cation and an anion of a strong acid, cation of a strong base and anion of a weak acid, cation of a weak base or small highly charged metal cation and anion of a weak acid, and finally the cation of a strong base and the anion of a polyprotic acid. Now, the next thing we're going to look at is the leveling effect. The leveling effect states that all strong acids and bases are equally strong in water. So that would tell us that hydrochloric acid, hydroiodic acid, and perchloric acid are all strong acids. And since they're in water, they all behave equally strong. All strong acids dissociate completely, essentially completely, to form hydronium ion. And the same with strong bases, they completely dissociate to form hydroxide. And in water, the strongest acid you can have is hydronium, and the strongest base is hydroxide. So water exerts what we call a leveling effect. Now, we'll find out that later on, it's possible to measure the fact that perchloric is a stronger acid than hydrochloric acid. But in water, you would not be able to tell the difference because of this leveling effect. Finally, we're going to look at a broader classification of compounds called the Lewis acid-base definition. A Lewis base is any species that donates an electron pair to form a bond. So that's an electron pair donor. For example, reacting with a proton. A Lewis acid is any species that accepts an electron pair to form a bond, like a proton. It can be a proton electron pair acceptor. An acid-base reaction is the donation and acceptance of an electron pair to form a covalent bond. So what we're seeing at this point is Arrhenius classified a small group of substances as acids and bases. but Arrhenius left out a lot of substances that had acid and base behavior. Bronsted-Lowry encompassed all of the Arrhenius acids and bases, but identified a whole other group of compounds that are acidic and basic. Finally, the Lewis definition broadly encompasses all the Bronsted-Lowry and Arrhenius compounds, but brings in a variety of other compounds. The product of a Lewis acid-base reaction is an adduct, a single species that contains a new covalent bond. A Lewis base must have a lone pair of electrons to donate. Any substance that is a Bronsted-Lowry base is also a Lewis base. A Lewis acid must have a vacant orbital, or be able to rearrange its bonds to form one, to accept a lone pair and form a new bond. Many substances that are not Bronsted-Lowry acids are Lewis acids, so the Lewis definition encompasses more compounds. It's more expansive. Here's a simple and common but important example. Boron and aluminum often form electron-deficient molecules. You saw this back when we looked in Chapter 10 at Lewis dot structures. We found that there were certain compounds that sometimes did not fulfill the octet rule, groups and elements in period 2 and period 3, and that's boron and aluminum. So, for example, boron trifluoride, BF3, has boron without an octet. And those compounds are typically not very stable, and so they're stabilized by reacting them with an electron pair donor like an amine. So here the base reacts with the electron pair acceptor, boron trifluoride, to form the adduct. Boron trifluoride is the Lewis acid. Ammonia is the Lewis base. Here we see Lewis acids with polar multiple bonds. So molecules that contain a polar multiple bond often function as Lewis acids. So for example, we have sulfur dioxide, and that can react with water. The electron pair of water is donated to the sulfur to form sulfurous acid. The oxygen atom is the electron pair donor, the base. Metal cations very often act as Lewis acids. So here we're seeing a divalent metal acid, like iron 2, can react with water to form an adjunct with water. Even if protons are not released, this is acting as a Lewis acid, and the water is acting as the Lewis base. And a classic example of metal ion, which is not necessarily an acid in water. So magnesium ion in water, though it will precipitate out as hydroxide. In chlorophyll, it's acting as an acid because it's an electron pair acceptor. That concludes our discussion of acid-base equilibrium.